I'm Gian. I'm from Imply. I'm going to be giving a talk called 3 Weird Tips for High Performance Analytics Applications. And let's get going. Let me talk. We don't have too much time. I'm Gian Merlino. I'm a committer and PMC member on the Druid project. It's a data project that started about 5-6 years ago. It's really built to power analytic applications, and this talk is going to be partially about the techniques we use in Druid to make that possible, and techniques you can use with Druid, and also about what work we're doing with that at Imply, which is a company I started a couple of years ago that's all built around Druid. Before I start, how many folks of you have heard of Druid or using Druid? Cool. How many of those hands are users? All right. Awesome. I love you guys. Maybe we'll mix use of more of you then. So agenda. First, intro to Druid. Then I want to talk about the virtues, 3 virtues and 3 weird tips. They're not that weird. Brevity, foresight, and flexibility. So first off, what is Druid? Druid is an open source, high performance, column-oriented, distributed data store. It's a mouthful. What does that mean? So we can unpack it a bit. High performance means we're shooting for low query latency and high ingest rates. So that's a key part of the DNA of our project. Column-oriented, best possible scan rates. Column orientation is the technology you use when you want to do an analytics database. It's common amongst all analytics databases. Distributed, we're typically deployed in clusters. The normal Druid cluster size is tens to hundreds of nodes. The biggest clusters are pushing 1,000 nodes. And then data store. It stores a copy of your data. It doesn't query data somewhere else. It loads a copy of your data into itself and then queries it. And what problem are we trying to solve? So the problem we're trying to solve we're trying to make analytic applications. And these are a screenshot of the analytic application that we make at Imply. It's an app built on top of Druid. And the idea with an analytic application is you want to be able to slice and dice, fly through your data. You want to be able to explore your data, build dashboards, and you also want to be able to see what's going on behind the dashboard. So, have a tile on the dashboard, pick it up, explore it, drill into it. And the idea is to figure out what's happening, build operational awareness, diagnose problems, and sort of, have a dialogue with your data. And to do that, high-speed queries are important. A lot of people are using Druid for this kind of thing. So this is all people that are from the Druid Powered By page. You can see a lot of big names there. Some of these were some of the earliest adopters of Druid, including Yahoo and Netflix. And a quote from Yahoo, they were one of the earliest Druid adopters. The performance is great. Some of the tables that we have internally in Druid have billions and billions of events in them, and we're scanning them in under a second. So that's the kind of thing that we're shooting for with Druid. So let's talk about the first virtue, brevity. So brevity is about compression. So one of the things we do in Druid to get good performance is we compress your data. We compress and index it. So in this part of the talk, I'm going to go into how we compress data in Druid. You can see here that we've got a sample data set of Wikipedia edits. So this is a timestamp of an edit, a page being edited, language being edited. So English Wikipedia, a couple pages, Justin Bieber, Kesha, and then some information about the user doing the edit. So they came from San Francisco, they came from Calgary, etc. They added and deleted some number of words. So the way that we're going to store this, like I said, we're going to store it columnar. So when I say columnar, I mean we're going to store every column independently, which is important because there's 2 ways of storing data in a data system. You can store it row-oriented, and you can store it column-oriented. Usually systems designed for transactions, for updates, that kind of thing, will store data row-based. They'll store all data from the same row together so you can update it easily. Systems designed for analytics, like Druid, usually store data in columns. And the reason for that is because your data might have dozens of columns, and for a typical analytical query, you're not going to query every column. It's going to be something like, I want the top 10 pages by number of hits. That's 2 columns, page and count. And you don't want to worry about loading data for the other 40 columns. And so by storing data separately, we only load data for the columns we need. And really, that's why this is the virtue of brevity. It's about only using exactly the data that we need to answer a query. So for the page column, we're going to store an array of, well, first storing a dictionary. So we're going to take, there's 2 values, 2 unique values, Justin Bieber and Kesha. We are going to call Justin Bieber 0 and Kesha 1, so they're integers. And then we're going to store each column as an integer array. So the page column is going to be an array of 0, 0, 0, 1, 1, 1. And the language column is going to be an array of all zeros because it's just 1 value. And then on top of that, we do compression. So the dictionary encoding is a form of compression. But then in addition, we do bit packing. And so, for example, these these dictionary IDs are integers. Integers are 32 bits. We're not actually going to store them at 32 bits. Here there's only 2 values. We're going to store them in 1 bit. So we'll store them in whatever number of bits is necessary. And then in the future, we're actually currently working in the Druid community on other kinds of compression. So there's frame of reference compression that we're looking at, run length encoding, which we're looking at. Run length encoding being great for situations where you have a very sparse column, that have mostly nulls and then a value, mostly nulls and then a value. You don't want to store you don't want to store a few bits for every null. You want to store, you want to say like I have 100 nulls and that's it. So there's a lot of cool ways to compress, columns. Different kinds of compression work different for different kinds of columns. Some work better for others than others. And one of the things we're looking at in the Druid world is having adaptive compression based on your data. So looking at the data and having, say, like, you may tell Druid, do I want to optimize for speed or do I want to optimize for size, and have it pick accordingly. And then finally, LZ4, optional. You can also optionally do an LZ4 compression on top of this. The reason you might want to do that is because you really want to optimize for space. Because what bit packing and RLE and P4 do, they look at slightly different aspects of the data than LZ4 does, so it can be beneficial to combine them. It's not always, and so that's why it's optional. And okay, what else do we do? So that's how we store your data. We store your data in this columnar compressed format. We also index it. So this is also part of the virtue of brevity. We don't want to even load. We split things up into columns, so we don't have to load columns we don't need. Now we use indexes, we don't have to load rows that we don't need. So we don't want to load, let's say we have a filter on the page column. We don't want to read the entire page column to do a filter, we want to have an index on the page. So we've got indexes on every column. In this case, the index for the page column is going to look like Justin Bieber goes to rows 0, 1, and 2, the first 3 rows. Kesha goes to 3, 4, and 5. She's in the second 3 rows. And those can both be represented as bit vectors, where the bit is 0 if the value is in the column, and the bit is 1 if the value, 0 if it's not in the column, and 1 if it is in the column. So then we can, at query time, we can look up the values, and then we can use those bit vectors to resolve which rows need to be scanned in other columns. So if you're saying, I want to know the top cities that are editing Justin Bieber, what we're going to do there is we're going to load the index for the page column, look at the value for Justin Bieber, get a list of rows out, and then look at those rows of the city column. So we're really minimizing the amount of data we need to read to do that query. And those bitmaps are nice because they can be combined across columns. We can do, if you have an and filter and or filter for page equals Justin Bieber and city equals San Francisco, we can get the bitmap from the page column, the bitmap from the city column, and combine them together. So it's nice for Boolean filters across columns as well. We also use compression for this. There's 2 kinds of compression we use. One is called roaring and one is called concise. I guess talking about those is a little bit out of scope for the talk, but they're both good in different kinds of situations. Roaring is better in most situations, so we make that the default. Second virtue is the virtue of foresight. Have any of you been to the talk yesterday? I think it was called Lazy Beats Smart and Fast. So that was about, part of that was about doing summarizations of data and saying, I'm going to group on sets of dimensions and I'm going to query the summarization that gets me the best performance. If I have a summarization that hits a few columns, I'm just going to query that one. That's what this is about. So we call it Rollup in Druid. It's a feature that we support in Druid. It's actually built in. And the idea is it's a projection of a table, also called an OLAP cube. And it can provide a series reduction row count. So let me show you how that works. So an example here, here's a data set of car sales. So cars are sold at a certain time, a certain make, model, year, sale price, sale fee. So how can we apply Rollup to reduce the size of this data set? Well, we can do something like this. So we took this data set that was originally 7 rows and made it 4 rows. It's a pretty substantial reduction in row size, almost 2x. It means queries are going to be almost 2x faster, which is great. What did we do? What we did was we split the columns into 2 types. One is called dimensions and one is called measures. So the dimensions, the white ones, colors are a little bit tough to see, but the first 4, time, make, model, year, those are fields we want to group and filter on. And the measures are fields we want to aggregate. So this is built around aggregations. So we don't have the raw data for the measures, but we have the ability to aggregate them. So we can now count rows. We can see the 3 3 source rows went to that first aggregated row. We've summed the sale price, so we can compute the sum sale price now. We can compute the sum of sale fee and the minimum sale fee. Out of this rollup, we can't compute the max sale fee because we haven't stored that measure in the rollup table, in the summarization table. So it's the value of foresight, because you have to have a little bit of an idea of what kinds of queries you're going to want to do. You have to know, I'm going to want to filter and group on these attributes. I'm going to want to do these kinds of aggregations. So with a little bit of understanding of what kinds of queries you're going to want to do, you can roll up on those dimensions and those measures, and in a lot of cases get a substantial reduction in row count. Like I was saying earlier, it could be 2 to 100x. Final one, flexibility. So the virtue of flexibility is about approximation. If you don't need exact answers, why bother with exact answers? Especially if you're trying to do an exploratory workflow, like I was saying earlier, you're trying to interact with your data, have interactive dashboards, analytic applications. A lot of times, fast response time is more important than having the exact answer, especially if the error can be bounded to something like 2-3%. So in Druid, we support a lot of approximate algorithms because we're built for this kind of thing. So we support approximate ranking. So that's top page by hits, approximate distinct count with set operations like intersection and A non B, and also approximate histograms and quantiles. The approximations all have in common that their memory is bounded or slow growing, so they're not going to need to use a ton of memory even with a high cardinality input, and also the error is sometimes bounded. So I'll go through an example here, HyperLoglog. How many of y'all are familiar with and use HyperLoglog? Cool. It's a really popular algorithm for distinct counting. It's been around for a little while. There's a whole family of algorithms called sketches that are algorithms that use these really neat memory structures to approximate answers to various questions. If you got time after the talk, if you get home, look up sketches online. They're really awesome. HyperLoglog is one of the granddaddies of sketches. It's one of those that's been around for a while. It's used for count distinct, and it's based on the bit independence of hash functions. So this is just sort of a flavor of how sketches work in general. Think about hashing a bunch of values. Let's say I want to do a distinct count of billions of values. And how am I going to do that? I'm going to take those billions of values, I'm going to hash them all with a strong hash function, or the decent hash function. It doesn't have to be super strong, it can be decent, murmur's okay. Assuming the hash function is decent and if the different bits positions are independent of each other, which is what you want from a good hash function, 50% of the values will start with 1, 25% will start with 0, 1, 12.5% start with 0, 0, 1, and so on. And what we can notice there is that, let's say that we've hashed things. Let's say we have a sketch that just keeps track of the maximum number of zeros we've seen at the beginning of a hash value. So we hash a billion things, and after a billion things, we expect to see whatever number of zeros in the middle of the hash value. So let's say we've hashed a bunch of things. We don't know what they are. We don't know how many. And we see the most zeros we've ever seen in a row is 4. So we see 0, 0, 0, and then 1, and that was the most zeros we've ever seen in the beginning. We're going to guess there was about 32 things. Because we would have expected to see that. We would have expected to see that one time if there were 32 things, and so we'll guess there were 32 things. Obviously, this is not super accurate. It can only guess powers of 2. You can think of a lot of cases where this is going to be super wrong. So what we do instead, that's the general idea, but the refinement to that is we do this a bunch of times in a bunch of buckets. So we actually have 1,000 different buckets. We're doing this 1,000 different times. In this example, we see only 64 buckets. There's a function, or there's a parameter called k. That's the number of bits you're going to use for the bucketing. The first k bits, let's say here k is 6, the first 6 bits determine what bucket number we're going to use, and the next bits are where we're going to look at the leading zero distribution. So we do a hash, we hash this value. This is going to go in bucket number 1, because the first 6 bits go to a 1, so it's on the first bucket, or second bucket, I guess. The first one is all zeros. And then we're going to store 1 there because there is 1 leading 0. And so we do this in a bunch of buckets, and then we apply some sweet math that's in the HyperLoglog paper, and out pops a cardinality estimation that you can actually prove has a bounded error depending on the k value. So the cool thing about this is the k value you can use to control what error you want, and then the total size of the hash, in particular, the amount left over after the k value, controls the maximum number of things you could possibly count. Because of course here, if you had a trillion things in there, you wouldn't have enough. You wouldn't have enough zero. You can only count 2 to the number of zeros you have left over. So that second part controls your max, and then the first part controls your resolution. And okay, so those are the three virtues. We got brevity, compression, foresight, rollups, and flexibility, approximate algorithms. I wanted to end by saying you can try this at home. Druid is open source. The company I work for, Imply, has a distribution of Druid. You can get it on our website. So it's available in both places. The Imply distribution additionally on top of Druid includes an application. Those screenshots I was showing earlier, I said Druid is used for powering analytic applications, and so we provide it out of the box. Or you can write your own on the Druid platform. You can also contribute. It's an open source with a vibrant community. As you can see up there on the Druid GitHub, we've got 212 contributors, 405 releases, a bunch of people started. We're on GitHub, so you can come on over there and join the development. We've also recently begun migrating to the Apache incubator. So that means Apache Druid is coming soon, which is really exciting for us. And finally, at Imply, we are hiring for pretty much everything, both the app and for Druid. So if you're interested in that, please come talk to me afterwards.
I'm going to ask the first question, as is my privilege as track host. One, have you thought about using Z standard along with LZ4 in that algorithm family, like optional compression algorithms that maybe are pluggable?
So yeah, we have thought about it. We ended up not doing it, partially because we are actually moving to a world where LZ4 is less necessary.
Gotcha.
The main reason we're using LZ4 now, so I was saying that LZ4 is good because RLE, run length encoding, and forward offset reference, and what was the other one? I don't know, bit packing. Those are all things that are specific to integers and are designed for compressing integer arrays. LZ4 is really general purpose. And sometimes LZ4 can find entropy that the other compressors can miss. But what we're hoping is that with this adaptive compression I'm talking about, there's a really amazing literature on integer array-specific compressions. Our hope is that with this adaptive compression we're talking about, and paired with implementing things from that amazing literature, that general-purpose compressors are just going to be a waste of time.
What's the easiest way to load Parquet files into Druid?
The easiest way to do that is we have a Parquet extension in Druid. It's a community contributed extension, so you can download it off Maven Central, I think. And it works with our Hadoop loader. So in Druid, we have three main ways to get data in. You can load using a Hadoop job. You can load directly in a batch mode from some file system or some object store like S3, or you can load directly from Kafka. And so for Parquet files, you probably want to run it. I mean, they're probably in Hadoop. That's usually where most Parquet files are.
Hadoop and S3, yeah.
Yeah, so you'd want to use the Hadoop loader functionality there.
I guess maybe just a question around use cases. So what inspired you to go and build Druid as opposed to using a lot of the solutions that were already available? Just, I guess what I'm trying to get at is if I'm thinking about incorporating Druid into my data stack, what are leading indicators that it might be the right technology versus just another piece of infrastructure that I now have to care and feed and that sort of thing?
That's a great question. We have actually a whole other talk about that. But the short version is that what we were looking for was something that could load real-time data, something that didn't require pre-computation of aggregates. And something that worked with high dimensionality and high cardinality. And what we were finding that we didn't find anything out there that hit all those buttons. And then the sixth thing we're looking for, or fifth thing we're looking for, I forget how many fingers I had, was something that could be online 24/7. We made Druid because we couldn't find anything that hit all of that was sort of able to be elastically scaled up and down and not take downtime, updated without taking downtime, and load data in real time and do all the stuff we want to do. I think that if what I see today with all the other solutions that are out there is that there's the situation that if you're in the situation where Druid is really the best choice, it's something that you're trying to build an analytic application, you're getting data maybe in real time, maybe from Hadoop, and you have a high dimensionality in your data and high cardinality in your data, and if you're facing a problem that's like, oh my god, I have some dimension or I have some column that's got millions of values and I'm trying to do ranking over it, I'm not sure how to handle this. Druid's got a lot of tools to handle that, a lot of them in the realm of approximation, stuff like that. But that's the area we're best at.
You mentioned that there are people running 1,000 node Druid clusters. Could you, this is a big thing, but is there a brief answer to the question of where does Druid fall in the CAP or PAC-elk theorems in terms of distributed systems and availability and consistency?
Yeah, availability for reads and consistency for writes. So in Druid, we have an interesting architecture where the reading and writing subsystems are very separated from each other. So we call it, the reading subsystem we call the historical nodes, and the writing subsystem we call the indexing nodes. And so the idea is that any data that was written more than about an hour ago is going to be on the historical side, and we really prioritize availability there. And any data on the real-time side, we prioritize consistency and loading from Kafka. For example, in order to attain consistency, the data may be unavailable for a little while or something like that, or we may block and not accept writes for a little bit. So, a system designed for super high availability on the write side would always accept writes, even if we can't handle them, we might throw some away. If we are not able to accept writes, we'll stop accepting them for a bit and kind of let the system flush out. If the indexing node crashes, then we store our Kafka offsets along with our Druid segments. So if it crashes, we back up and reread from Kafka exactly once. So we got kind of an interesting space there because we split the architecture. But we did that because we're trying to both provide good operational properties around high uptime for building an app on, and also reasonable guarantees around, you want to make sure that the data that you have in Druid matches what is in your source system, like Hadoop or Kafka. We really try to make that happen.